All right, I'll even turn on the projector. And turn on the slide set from current slide. And let me go over just a couple of announcements with you. I think you've heard them all before, but just in case, for those who are not here. Last night at midnight, or this morning at midnight, whatever that may be, was midterm, okay? And at some point, I haven't seen that they posted it yet, but at some point they usually ask for us to post midterm progress reports. And that's where I put anyone who has a D or F at midterm. And right now, in this class, I have 5 people who have turned in something, but that's only 4 people. 5 things have been turned in, but it's only by 4 people. So that means the other 3 people have turned nothing in. So I need something in before probably next Tuesday. Like I said, they haven't stated when this is due. Usually they give us a week, and that would be a week. So I just need something to be turned in. Otherwise, I'm going to have to put down an F at midterm. Not that it makes any difference or anything, except you might start getting phone calls or emails or something about, do you need tutoring? Do you need counseling? Do you need help with transport? Whatever. So better to save that hassle and get stuff turned in soon. All right. Another issue with that is that I'm not going to be on campus at all on Friday. I've got a meeting down in Mobile. I've now learned that it's starting at 11:30, so I definitely have to be on the road by 7 or before 7, and to be there by 11:30, and the meeting goes until 3. So for a 3.5-hour meeting, I'll be driving 4 to 5 hours down there and 4 to 5 hours back. So 8 to 10 hours on the road for a 3 to 3.5 hour meeting. And the half hour is going to be lunch, so that's not much of a meeting time anyway. But anyway, I've got to be there, so I will be there. Next Friday, I won't be on the Birmingham campus 8 to 11. I'll actually be on this campus at 8, but then I'll be at 8:15 across the road at the eye doctor. I've got an appointment there. I thought it was going to be at Eye Foundation Hospital. They said, no, he's going to be at Birmingham West, or UAB West. I said, well, that's right across the street from where I work. So I said, fine, I'll take that one. And I tried to get it later in the afternoon, but couldn't. So I got it as early in the morning as I could. And that was 8:15. So as soon as that is over, then I'll probably be heading back to Birmingham West. So anyway, that's all I know about now. Any questions from you? Okay. We are in Chapter 11, Vectors in the Geometry of Space. We will be in 11.3, but we've still got example 7 to do in 11.2. Let me see if I can find a slide. That's probably going to be my best one. So let's go back and do on this one. Example 7 on page 766, Chapter 11, Section 11.2. A television camera weighing 120 pounds. So, by the way, that is a force. Weight is a force. So, I'm going to call it F sub W is 120 pounds, I believe it said. Yeah, 120 pounds. It's supported by a tripod. Okay, as shown in the figure. So it's basically something like this, the big old camera here. Okay. Represent the force on each leg of the tripod as a vector. Okay. Now, I haven't drawn a very attractive looking tripod. Maybe this one should come in a little bit there. Let me erase that one. And what they do is set up the grid so the camera is right over the origin, okay? And we'll have the x-axis going like this and the y-axis going like that, okay? Trying to get it sort of three-dimensional. Okay. Now, I didn't draw that well either because they drew their Q1 as being on the negative y-axis, or negative y-axis. So let me change my axes around a little bit. Okay. Try to do this anyway, as I'm not very good at this. Okay, this is right over the origin, and we'll have the y-axis coming supposedly down here, and this is the negative y-axis. That would make that the negative, or the positive y-axis. This the, I haven't drawn this well at all, the x-axis and the y, so x, y, yeah. Okay. I should have drawn the axes first and then drew the tripod. Let me try it that way. That will be a little bit better. Goodness gracious, I didn't know this was going to be this difficult. All right. Let me try it one more time. Maybe more than one more time, but try it. Okay. We have the y-axis coming something like that, and the x-axis something like that. Okay? So this is positive x, positive y. Okay, right-hand rule. Okay, the tripod is sitting so that on negative y is a foot, on here and here are 2 feet. So we'll have it coming up like this with the camera on top. That might be a little better. All right, now they have fixed it so P up here, which is the camera, why they named it P is just because they named all of them. It's going to be at 0, 0, 4. So they do have a z-axis, okay, but it's at 4 units up there. Mine's definitely not to scale. This is a Q1 over here, and Q1 over here is at 0, 0, negative 1, 0, okay, because they have the negative y and 0 on z, and they have Q2 over here at, now these are points, root 3 over 2, 1/2, and 0, root 3 over 2, 1/2, and 0. And this is Q2. And back here is Q3. And this is negative root 3 over 2, 1/2, and 0. Okay. Represent the force exerted on each leg of the tripod as a vector. Okay. The weight, which is directly below here, was 120 pounds. That's an ugly B. Okay, 120 pounds. So, what we have to figure out, and that's pointing straight toward the origin. So we know this is 4 up, 1 out, okay, and there's the angle there. And now we're making an assumption here, and I'm going to need to justify the assumption. Assuming that these 3 legs are each supporting an equal amount of weight, okay, and the reason we can do that is these appear to be on a unit circle, and let's see. Square this, you get 3/4 plus 1/4 is 1. Square this, you get 3/4 plus 1/4 is 1, and that, of course, is 1. So they are equal distant from the origin, okay? And they're on the unit circle 1. Now, that's just really clever how they did that. So let me see if I can approximate a unit circle there. Okay. Now, since they're, and the camera's directly over the origin, So that would mean each leg is supporting the same weight. Okay? So basically what we have is 40 pounds on each leg. The 40 pounds would be pointing straight down, and then you have to determine the component of that 40 pounds in the minus, I guess, I don't know why I have a 1 there, but that should be a -1, okay? And, okay, we'll go from there. So, the magnitude of the weight is 40 pounds, okay? And the vector, here's Vince, double the class size. Okay, we're doing the example 7 at the bottom of page 766, okay? It's an ugly rendition for sure, and it's not to scale. The camera's 4 units up, it weighs 120 pounds. The legs are just 1 unit from the center, which obviously is not to scale, but I'm going to try to do that. Okay, so you got, this leg is supporting 40 pounds because they're a tripod, equal weight, equal distribution. So the 40 pounds is in this direction, but it's, you have to resolve that. This, of course, is your 90-degree angle. So your opposite side is going to be 40, okay? The adjacent side is 1, in this case a -1. No, I'm sorry, the opposite side, okay, depends on which angle you're talking about. Let's see. Okay, here, okay, we'll do it this way. These are the 3 forces. We know that each of them are 40. Okay, let's call this F1, F2, and F3. Okay, I know this is hard to read in the red up there. I'm having to work around all the things. So, from the point up there, your F1, the direction of F1 anyway, is, and the x direction is 0, well, final minus initial, okay, so that would be 0 minus 0 is 0, -1 minus 0 is -1, and 0 minus 4 is -4. So that's, I should be doing angle brackets because these are indeed vectors. Okay, that's the direction of it. Okay, obviously not a unit vector either. Okay, and okay, let's just do the other two. F2 would then be √3/2, 1/2, -4. Okay, and 3, force 3 would be -√3/2, 1/2, -4. Okay, because it's, that vector is Q minus P, basically. The vector F1 is PQ, or that's the direction of it. Okay. We know its magnitude, though, is 120. Obviously, these are not, the same magnitude. In fact, if you did this, you'd do the square root of 1 squared plus 4 squared. That would be 17. This should be 3/4 plus 1/4 plus 16 is 17. So each of those, the vectors as written, have a magnitude of 17. We need to have them 40. So basically, we need to multiply by 40 over 17, I believe it is. For some reason, they don't do it that way. Well, no, this isn't quite right either. Because the 40 is in this direction, not those directions. So, and they're not using the angles. I thought they were. They're not using those. So the 120 pounds, well, no, they are using it. And this, by the way, is a minus 40, the weight downward, because everything's directed upward. So basically, these are the direction. To get the actual vector, you multiply by its magnitude, and the magnitude is c, okay? But we also know that magnitude, c, is equal to, no, I'm sorry, that's not quite right, but I'll get to that in a minute. C is, okay, because that's not quite right. The C's are correct, and that's what the vector would be then. But we need to determine what C is. Now we know the sum of these three vectors needs to be 120 to the south. Or the sum of any one vector, the magnitude of that would be 40. And I think that's how they're going to do it. Yeah.
Would the magnitude be the square root of 17?
Okay, well, we know that the weight is 120 pounds. So the component, the magnitude of the force downward of each of those vectors is 40, because, you know, there's three of them adding to only the downward component. Not the vector itself, the downward component is 40. But that is, you know, the total weight on it, because there's no weight right or left or up or down. You know, it's only, I mean, just straight down. Now, because for each one of these, the magnitude of the vector, okay, I'm trying to see where I know these numbers are what they've got, okay? All three legs have the same length, total force distributed among the three legs. You know that the magnitude of each one of these is the same. There exists a constant such that this is true. We know that. Let the total force exerted by the object be given by, and that's what we got here too, F, the total force is equal to 0, 0, 120. Okay. Now, this is where they're getting it. Now, I want to point something out to you. If you add these components, C times 0 plus C times root 3 over 2 plus C times minus root 3 over 2, that adds to 0. Of course, okay? And this one, minus 1, plus 1/2, plus 1/2, that adds to 0. So the whole force is adding to 120. So therefore, you add this and this and this. These components add to 0. These components add to, well, that's a total of, each one of those is equal to, the three of those add to 120, okay? and then divide by 3 and you get 40 each. So you know that the negative 4 has to be C times negative 4 has to be that third of this, which is 120. So that means C is equal to negative 10. So now we've got the three vectors. F1 is equal to 0, 10, 40. F2 is equal to 5 root 3, 5, 40, and F3, that should have a vector symbol over it, F3 is equal to negative 5 root 3, 5, 40. So our three vertical components add to 120, which it's got to add, and these three add to 0, plus 5 root 3, minus 5 root 3, that's 0, 10, oops, that's a minus 10. Yeah, sorry, the minus 10. Yeah, I wrote it as a minus 10. Okay. Well, no, I just did. Minus 10 plus 5 plus 5. No. I got it backwards. That should be the plus 10 minus 5 minus 5. Sorry about that. I wrote them backwards. I had this one right to begin with. I forgot to do a minus 10 here. So that's a minus 5. Oh, yeah, that's right now. Except for this sign. That's the minus, this is the plus. Okay. Now I got it right, I think. Okay. So the F1 is 0, minus 10, minus 4. Oh, that's right. That's where I messed up. This is a minus 40, because that's a minus 120. Sorry. So that makes this a positive 10, so I had it right before. Minus, okay, wait. Zero, minus 10, minus 40, because it's a total of minus 120. That's it. Plus that minus 5, minus 40. No. These two are the same. This is minus on this one. And this is a plus and a minus on that. I think that's right now. Let's see if I got it right. 0 minus 10 minus 40. 5 root 3. No. I had it right the last time. Well, I don't need that. Plus, 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 minus. Still not sure that's right, but it's a minus plus, sorry. This is the minus, and that's the plus. Okay, now I got it. Okay. This one's 0 minus 10 minus 40, because we're taking down to be negative. The next one is 5 root 3, 5 minus 40. And the next is minus 5 root 3, 5, and minus 40. Got it. Kind of crazy, that one. And what you got to do, of course, we came up, this is what they were wanting, the directions of the vectors here. And then the constant had to be such that these three, the downward force has to be minus 40. So that made C positive 10, okay? And then you multiply positive 10 by each of those. So you keep the sign convention the same But this becomes minus, minus, this becomes plus, minus, minus. Plus, plus, minus, that's minus, plus, minus. So, yeah, that's what it works out. Sort of a pain in the neck problem. Sorry about that. We should have just skipped it. Okay. I think I've already told you, homework assignments here, do either 5 or 7 or both. They both should be at Calc Chat. Either 9 or 11, they both are at Calc Chat, 9's at Calc View. Any of the odds 13 to 23, they're all at Calc Chat. Do either 25 or 27, they're both at Calc Chat. 25's at Calc View. Either 29 or 31, both at Calc Chat. Either 33 or 35, both at Calc Chat. 33's at Calc View. Any of the odds 37 to 41, they're all at Calc Chat. 39's at Calc View. Either 43 or 45 or both, they're both at Calc Chat. Do 47, it's a Calc Chat. 49 is a Calc Chat. Either 51 or 53 or both, they're both at Calc Chat. 51's at Calc View. 55's at Calc Chat. 57's at Calc Chat. Either 59 or 61 or both, they're both at Calc Chat. Either 63 or 65, they're both at Calc Chat. 63's at Calc View. Either 67 or 69, they're both at Calc Chat. 67's at Calc View. Do 71, it's a Calc Chat. Any of the odds 73 to 77, they're at Calc Chat. Either 79 or 81 or both, they're both at Calc Chat. 79's at Calc View. 83 or 85, they're both at Calc Chat. And 87's at Calc Chat. And 89's at Calc Chat. Oh, there's more. Yuck. 91 and 95 are writing exercises. If you want to look at them, you sure can. By the way, I need research papers in sometime soon, okay? Then 95 should be at Calc Chat. 97 should be at Calc Chat. 99, another one sort of similar to what we just did at Calc Chat. There's a load support problem at 101. That should be at Calc Chat. A geometry problem, 103. And that's it. All right. Now, let's clear this screen and get going on 11.3. Like I said, let's back up. 11.3 is the dot product of two vectors. This is much, well, pretty good stuff. Really not that hard. Okay? Objectives here are to use the properties of dot products of two vectors. We'll find the angle between two vectors using the dot product. There's actually two definitions for dot product. And the book gives one first and then another one later. When I learned them, I learned the second one first and then the first one later. They both are co-equal. But that's what we'll be doing there. We'll find the direction cosines of a vector in space, which is sort of a new concept. We'll find the projection of a vector onto another vector, which is using these new concepts. And we'll use vectors to find the work done by constant force, which is sort of what we were doing at the end, but we'll do it using dot products now. Okay. So what in the world is a dot product? If you remember, we talked about negating a vector, that's just changing all the signs. Scaling a vector, which means multiplying by a constant. Positive, it stays in the same direction. Negative, it goes in the opposite direction. A bigger number scales it up. A smaller number reduces it. Okay, so we've done that. Then we talked about adding and subtracting vectors, which is just about how you expected. We talked about multiplying vectors by scalars, and we talked about associative and distributive, sort of distributive, associative and commutative properties. All those were fine. But one thing you might notice, we never multiplied vectors by vectors. It was always a scalar times a vector, and all of our associative and commutative things we're doing with scalars and vectors. In these next two sections, we're going to talk about how we multiply vectors. Well, vectors are multiplied in one of two ways. Okay? This is the first one that's called the dot product. Now, these get their names from way back in, I don't know, this is what I assume it is. Way back in math, like when you first started learning multiplication, we said 7 times 3 equal 21. We used the time sign. And we used that up until we got into algebra. And then once we got into algebra, our favorite variable of all times was an x. And then a times sign got not to be a very good thing to use because you might think it's an X. Or you might think the X is a times sign. So, whoa, we have problems, Houston. So what do? We went to using a dot product to represent 2x dot 3y, and that's how we multiplied algebraic expressions. Well, since we had two ways to represent multiplication, the old x and the old dot, when we got to doing vectors, or at least this is my theory on it, they said, well, we got two different ways to multiply vectors. Let's call one the dot product and one the cross product. Okay? So we're going to start with the dot product, which is in many ways a little bit easier. It's pretty straightforward. It says you have studied two operations with vectors, vector addition, vector multiplication, by a scalar. And by the way, subtraction is counted with addition. Each of which yields another vector. In this section, we're going to study a third vector operation. This is the dot product, which is multiplying a vector by a vector. But guess what? The answer turns out being a scalar. So before, when you multiplied a vector by a scalar, you got a vector. Now you multiply a vector by a vector, you get a scalar. Okay. Now later when we do the cross product, you're going to get a vector. So but this one, you're going to get a scalar. So here's the definition of the dot product, or at least the one they use first. The dot product of some vector u, which is u1 comma u2, dotted with some other vector v, which is v1, v2, here's what you do. The dot product of these two vectors, these are both vectors. Notice over here, nothing's bold. Everything over here is a scalar. What you do, you multiply the first component times the first component, and then add to that the second component multiplied by the second component. So it's the sum of two products. Okay? That's what the dot product is. Now, if you're in three dimensions, u being u1, u2, u3, and v being v1, v2, and v3, the dot product of those two would be u1 times v1 plus u2 times v2 plus u3 times v3. So that's what a dot product is. It's multiplying the corresponding components and adding them to the next corresponding components until you're through with components. So obviously you have to multiply two-dimensional vectors by two-dimensional vectors, three-dimensional by three. You can't do a 2 by 3. No, that won't work. All right, so here are some properties of dot products. Okay? U, V, and W are all three vectors in the plane or in space. They could be two or three dimensional or more, but we're not going into that now. CB, our favorite old scalar. Okay. Now the first of these is the commutative property. It doesn't matter which order you multiply, because that's going to be U1 times V1. This is going to be V1 times U1. Those are just numbers. They can be commuted, and so add to that V. So it doesn't really matter. U dot V is the same as V dot U. They come out scalars anyway. That's commutative properties of dot products. Or associative property. Well, no, this is more of a distributive property. Okay? Now, this one, you're adding these two, dotting it with these two. So you add these two, you get a vector dotted with that, and you get U1 times V1 plus W1 plus U2 times V2 plus W2 plus U3, if you had 3, times V3 plus W3. But if you think about that, the U's multiplied by both of those, so you can just distribute it. U dot V, and by the way, this is a vector, that's a vector, but you dot them, you get a scalar. Well, you dot these two, you get a scalar. You dot these two, you get a scalar. You sum of two scalars is a scalar. So the distributive property is what I would hope you think it should be. U dot V plus U dot W. Perfect. Okay? Now, this is kind of another Weasley kind of associative property. If you have a dot product of two vectors, okay, it's going to be a scalar. Multiply it by scalar, you're going to get a scalar, okay? But what this says is you can multiply one of the vectors by the scalar and then dot it with the other, like this. or dot the first one with the scalar times the second. Either one of those will work. So you can associate the scalar with either vector. You don't associate them with both. It's just either one. This is not a distributive. This is a associative. Is that someone? Yes, it is someone coming in. Then. Okay. All right. Now, the fourth one doesn't really have a title, though I think it could. It's the zero vector dotted with any other vector v. Okay? This is vector times vector dotted with vector. Obviously, it's got to be a scalar. And what scalar will it be? The number 0. Why? Because this is 0 times v1 plus 0 times v2. And if it's three-dimensional, plus 0 times v3, that's 0 plus 0 plus 0. 0. All right. Now, here's another one that you might find interesting. When you dot a vector times itself, you get the square of its magnitude. Because think about it. You got v1 times v1, that's v1 squared, plus v2 squared, plus v3 squared. Well, the square root of that is the magnitude. So square it, and you lose the square root, and that gives you the magnitude squared. So, this gives us another way to get a magnitude. Dot the two vectors together and take a square root. And that would give you the magnitude. All right. Now, let's do example 1. U is the vector 2, negative 2. V is the vector 5, 8. W is the vector negative 4, 3. What is U dot V? Goodness, I wish they hadn't done that for you. Okay? Well, I guess. They just wrote it down for you. See it? Oh, man. I would have had you write it. But, so how do we do that? Anybody? Dot product of the two vectors.
v1 times v2.
And what is that?
I mean, v1 times, what do we do first?
U1 times V1, right?
v1 times v1.
And what would that be?
2 times 5 is
10 plus
10 plus
negative 16, and that would be
negative 6.
negative 6. And dot products are scalars. It doesn't say only positive scalars, it says scalar. And negative 6 is just as good as any other scalar. Okay? I think I'll have to erase this to go to the next one. That would be 2 times 5 plus a negative 2 times 8. And that's equal to negative 6. Good for them. Okay? Next we're going to do U dot V times W. Oh, what in the world do you think that could mean? Ooh, yeah, they already wrote it for you. Okay? U dot V we just did. That's a scalar. Multiply a scalar times a vector. That's just scalar multiplication. So what would that give you? Here's W. And there's U dot V. See it?
Is it negative 40?
Okay, you're not doing a dot product, you're doing a scalar product. So you're multiplying a scalar times a vector, you get a vector. So here's a scalar, there's the vector. Negative 6 times 4 is?
It should be 24.
It's not negative.
Negative 24.
It's not negative.
I say it's 24.
Oh, 24, okay, I'm sorry. 24, comma,
Negative 18.
negative 18. It is, oh, okay. They just did the negative 6 times negative 4, 3. And that comes out to be 24, negative 18. That comes out of scalar because you're doing I mean a vector because you're doing a scalar times a vector. All right, let's see what C is. All right, now this one they already started for you. I don't know why. It didn't matter how you did it. Let's do it the way they did first. This will be U, which is 2, negative 2. And we're going to dot that with 2 times V. And what's 2 times V? Can you do it? 2 times V. There's V. Two times 10, 16. Okay? And you dot those two together, and what do you get? 20 minus 32, which is negative 12. Okay, let's do it the other way. Let's do 2 times, we're going to first dot U, which is 2, negative 2, dotted with V, which is 5/8, and see what that gives us. 2 times, and what's the dot product of those two? I think we just did it, didn't it? Negative 6. And what's 2 times negative 6? Negative 12. Ding, ding, ding. We got it. Same as before. Okay? So let's erase this. Any questions yet? Dot products are pretty straightforward, pretty easy. Just keep straight what you're doing. Okay, let's see about, oh, here they show it. 2 times negative 6, which would be negative 12. But I showed you the other way, and you came out negative 12 as well. All right. What is, I haven't done that. What is magnitude of W squared in terms of dot products? One of the rules, properties we just had. Magnitude of W squared.
W times W?
W dot W. Okay. Yeah, W dot W. And W is negative 4, 3. Dot it with itself. What would you get?
16
Plus?
plus 12.
Plus what?
Plus 9.
Yeah, 16 plus 9?
And 25.
25. Okay. They showed the dotted there. And they also showed that is equal to that. Okay. Which is equal to 25. It took them long enough. Is there an E part? Notice the result of part B is a vector quantity, whereas all the other 3 parts are scalar, because these, all 3, were basically just dot products. In fact, that is a dot product every time it's that. Whereas this one was a dot product, which gives you a scalar multiplied by a vector, so that made a scalar, what they call a scalar product. And that's a vector. Okay, there's example 1. Let's move on to example 2. The angle between 2 vectors. What has this got to do with what we were doing anyway? Well, guess what? The angle between any 2 non-zero vectors. Don't ever try to get an angle between a zero vector and something else, because a zero vector has no magnitude. How could you get an angle from it? So it has to be 2 non-zero vectors. Is the angle theta that's always no greater than pi. Okay? Because okay, I'll do it this way. There's an angle that's less than 90. There's an angle that's right pretty close to 90. This was greater than 90. This was 180. If you get down here, you're talking this one. Again, less than 180 or less than pi. So it's always the smaller angle between the 2. Don't do the one that, see, these are obtuse, so this is beyond obtuse, okay. All right. So the angle between the 2 non-zero vectors, the angle between 0 and pi, between their respective standard position vectors is shown here. I think I understand what they're saying. Usually when I see standard position vectors, I guess I see what I mean. If this is 0, then that would be vector V, that would be vector U, okay. Both from the origin, okay. Now, that vector V, that vector U, how in the world do we find the angle between them? Okay? Now, things to note. This is not necessarily a 90-degree angle, so don't make that assumption. Even though it looks like it could be close, it's not. Neither one of these are. We're not dealing with 90-degree angles now. Any old vector between any other vectors definitely doesn't have to be that. Okay. So, they also throw this in here, and there's no obvious reason why they do that at this point. But I think maybe it will show up. Okay, here's the theorem. If theta is the angle between any two non-zero vectors u and v, and theta is between 0 and 90, and 0 and pi, not 90, 180 or 0 and pi, then here's the other definition. Well, this is the definition of a dot product, but it will lead to that. The cosine of the angle in between is the dot product between the two divided by the product of the magnitudes. Okay? That's going to be the cosine of the angle in between. Notice that magnitudes are always positive. So that denominator is always positive. Okay? The numerator, u dot v, will have the same sign as the cosine. Because if these are always positive, then this will determine the sign of the cosine. The SIGN sign of the cosine. Okay. Oh, man. Now, here is figure 1125, shows possible orientations of two vectors. If u and v are exactly pi apart, then the cosine of these, if you go back to that definition, let's just say that both u and v, for no other reason, let's just call them unit vectors, but they don't have to be. They could be any vectors. Magnitude of u times magnitude of v. Let's just, don't say, let's just assume they're the same length. They don't have to be that either. Okay? The angle in between is theta. Theta, and that happens to be pi. The cosine of the angle in between, the cosine of pi is -1. Now, cosine starts at 1, goes down to 0 at pi halves, down to -1. So there's your cosine of -1. Okay? So, well, we won't say anything more about the dot product. But notice on this one, you're less than pi, but greater than pi halves. So you're an obtuse angle over here. Well, over here, if it was out here, theta would be the cosine theta would be -1. Up here, it would be 0. So in between those two, it's got to be between 0 and -1. So cosine theta is between 0 and -1. Now, when theta is a 90-degree angle, the dot product, okay, I'm sorry. They didn't say anything here too revealing. They just say opposite direction. Okay. If you were really saying something revealing, you would say the dot product is definitely negative. Okay. It's not saying a lot, but it is. Here, the dot product is also negative. Okay. Now, if you think about this, though, the magnitude here and the magnitude there, that's going to be your denominator. That's your numerator. The cosine in the second quadrant is negative. That's how you know that's negative. But this dot product is going to be less than the sum of those two together. Now, we haven't done that yet, but it will come out being that. But when you're up here, 90-degree angle because the dot product is the same sign as the cosine. Well, the cosine of pi halves, or 90 degrees, is 0. So that means the dot product has to be 0. Now that's going to lead to something which you're going to do in a couple of more pages, okay? I'm going to say it first, okay? The projection of this vector on this vector would be a negative. Notice this, negative. Something less than that magnitude, but still, if you're projecting this downward onto the horizontal axis, there would be the projection. Project that down on the horizontal axis, you're at the origin, 0. Project this onto here, and you're something less than 1, but you're positive, because this is a positive projection. Okay? The u dot v is greater than 0, but technically less than 1, too. And the cosine has to be between 0 and 1. Cosine's always between -1 and 1, so not a surprise it has to be less than 1. And here when they're in the same direction, the theta is 0, so cosine of theta is 1, so this mapping onto that would just be that. Okay, it's the same length as u to begin with. Now that's jumping ahead a little bit. Okay. From theorem 11.5, let's go back and see, 11.5 is this one. Angle between two vectors, cosine theta is the dot product divided by the product of the magnitudes. Okay? You can see that two non-zero vectors meeting at right angles if and only if the dot product is 0. That's important. That is something you're going to use a lot. If the dot product of two vectors is 0, they've got to be perpendicular to each other, and we call that orthogonal. So the definition of orthogonal vectors, any two vectors u and v are orthogonal when, if and only if, u dot v is 0. If u dot v is 0, they're orthogonal. Okay? Meaning perpendicular.
Perpendicular.
And orthogonal means the same thing. Is that what you're saying?
Well, I was talking about orthogonal.
Orthogonal and perpendicular, yeah, they mean the same thing. At right angles to each other is another way of saying it. I mean, there's a lot of ways to say that. Okay. Here's example 2 then. Goodness gracious. And this is one of those that you can see larssoncalculus.com for an interactive version of this type of problem. And I've gotten so I always check to make sure the problems are the same, because in my pre-calculus algebra book, written by the same author, published by the same company, every now and then I run into one that aren't the same. The slide set and the one in the book are different, and I don't know where. Okay. It says find the angle between each pair of vectors. Here's 4 vectors. 3 minus 1, 2 is u. V is -4, 0, 2. W is 1 minus 1 minus 2. And Z is 2, 0, -1. So the angle between each pair of these vectors. Now they didn't do, well, I guess they did do them all. U and V, U and W, V and Z. They didn't do U and Z and V and Z. So V and Z they did. They didn't do U and Z. Okay. That's okay. We'll let them live without it. What's the angle between the two? So what's the angle between these two? Cosine of theta is equal to what? Give me the formula or the definition of dot product that tells you the cosine of the angle. U dot V, and they're both vectors, remember, divided by magnitude of U times the magnitude of V.
So U dot V is different than U times V?
Okay. Now, as I said at the beginning, but we haven't done it, there's two ways to multiply vectors, dot products and cross products, okay? So to get you used to, if you say times, I don't know which one you're talking about. Well, obviously I do now because we're only doing dot products, but get used to saying rather than times, because times is ambiguous when you're dealing with vectors. Say dot product, dotted, or crossed, okay? One or the other. And I got 4 lines awfully close together down there. It's hard to see. So there's at least 4 calculations you need to make here. One's a dot product, 2 are magnitudes, and 1 is a multiplication and division. So I guess that's actually 4 or 5 or whatever. 5, I guess it is. So what's the dot product between those two vectors? Negative 12
plus negative 1.
How did you get that? U dot V.
Negative 1. Oh. I was adding.
Yeah, that's
That'd be plus 0.
plus 0. Got it?
Plus 4.
Okay. Over. Now. Goodness, my head is so clogged. Let's do the magnitude of U. Now remember, there's 2 ways to do it, and they really are the same way. It's U dotted with itself is the magnitude squared, so it's the square root of U dotted with itself. So that would be the square root of
Square root of 9.
right?
Plus 1.
Okay.
Plus 4.
Okay, let me see, make sure. 9 plus 1 plus 4, okay. 9 plus 1 is 10 plus 4 is 14. Square root of 14 times, we're doing V now,
And, square root of 16 plus 0 plus 4.
plus what?
Plus 4.
Right. And that would be second?
Square root of 20.
I can't hear you.
The square root of 20?
Yeah, square root of 20. Okay. That's what I was listening for. All right. We can clean that up a little bit, and I think we will. But let's do the numerator first. What would that be?
16.
Negative. Negative 8 over. Now, I do want to straighten this up a little bit. I can factor out a 4 from the 20, so that would be a 2 root 5. Okay? I can't factor anything out of the 14. 2 times 7, but they don't come outside the radical. So that would be 14 times 5, I believe, is 70. So 2 root 70. Now, there aren't any common factors there, I don't think. All right. So that's pretty ugly. Let's clean it up just a little bit. Minus 4 over root 70. And I'm perfectly happy to leave it like that, but if you really are particular about it, you could say minus 4 root 70 over 70, which to me is more complicated than it is there. Okay. It looked like there were lots of opportunity for me to make an error there. Yeah, negative 4 over root 70. That's how they left it. They left it in this form. See, they're sort of forgetting about no radicals in the denominator. Okay, so that was the A part. Let's do the B part. U and W. The cosine of angle theta between U and W would be what? Okay, U and W is what? 3?
3 plus 1
right?
plus -4.
Yeah, -4. That, to me, looks a lot like a 0, doesn't it?
Sure.
I don't think we need to go much further. This is going to be 0. So what can you tell me about those two vectors?
They are.
What's that again?
I was thinking.
That's without doing anything to the denominator. If the numerator is 0, though, the entire fraction is 0. And if the cosine of an angle is 0, what does that tell you? Yeah, they're perpendicular, or the word now orthogonal with each other. So it doesn't matter how big or small. Yeah, it just, if the angle is 0, I'm sorry. If you, trying to think if that, what an application for this was. I can think of several, but it's sort of beyond. Let's just hold off of that until we get that far. Let's do the C part. We just stopped right there and said that one. Between V and Z, okay, cosine theta between V and Z. I'm going to put it here because I get lost on which ones we're doing. Okay, what would that be? V and Z. The numerator is the dot product between the two, and what's that?
-8.
Second?
-8.
-8 is the first part.
Plus 0.
Yep.
Plus -2.
All right. So what did it come up being?
-6.
-10. Okay, divided by. Now we got to do the magnitudes of those. And I guess it's easier just to do the square root things. And what's the magnitude of V? Did it a little earlier, I thought. Square root of 20. 16 plus 4. What? I put bars there, we don't need it. Square root of 20 times.
Square root of 4 plus 0 plus 1.
If you said something, I didn't make it out.
You need the square root of 5.
Square root of 5, got it. Now again, when we did square root of 20, we said that was 4 times root 5, and 4 times root 5 times root 5 would be what? Second?
20.
Yes. So that would be 20. And what would your whole fraction be then? Negative 1/2. Which is a very good thing. And by the way, let's go back to this one. Minus 4 divided by root 70. Anyone just have a guess about what root 70 is? Between what two numbers?
Between 8 and 9.
Yes, exactly. Because root 70, or 8 squared would be 64, 9 squared would be 81. So this is between 8 and 9, a little bit closer to 8 probably than 9. That makes you feel warm and fuzzy inside because the denominator has to be greater than the numerator in magnitude, right? Because cosine has to be between minus 1 and 1, and this is between minus 1 and 0. Fantastic. Okay? This one, you know, is between minus 1 and 1. It's between minus 1 and 0 as well. 0 is between minus 1 and 1. So all three of these have valid sounding cosines. If you ever come out with a cosine to be something like 1.3, go back and check your work because it isn't. It can't be. It won't be ever. Okay. Now wait a minute. I must have messed something up here. That was 2 root 5, not 4 root 5. Duh. And 2 times 5 is
10.
Is what?
10.
10. And so this will be a minus 1, not minus 1/2. Okay. All right. Sorry about that. And what else we notice here is that since this is a minus 1, that means they're in opposite directions from each other. And sure enough, this is exactly a multiple of that. Negative 2 times this gives you that, right? Negative 2 times 2 is negative 4. Negative 2 times 0 is 0. Negative 2 times negative 1 is positive 2. Yes. So those are multiples of each other. They are collinear. They are dependent vectors. One depends on the other. Okay. Now, I told you, okay, let me back off of here. Let's see how they did this example too. Okay, the cosine of the first u and v is the dot product of u and v divided by the magnitude of u times the magnitude of v, which would be minus 12, exactly, plus 0, plus 2. That would be a negative 8 divided by square root of 9 plus 1 is 10 plus 4 is 14. And 16 plus 4 is 20. Okay. So there is our angle. Well, cosine theta is equal to that. And we'll carry that a little bit further. Oh, we didn't do that, did we? We didn't find the angle. We just said the cosine of the angle. How do we get the angle? That's where we stopped. Sorry about that. Cosine of theta is negative 4/70th, but they're saying find the angle between each pair of vectors. How would you do that then?
by 1.
Okay, if you divide it by 1, you still get the same value.
Yeah, that's right.
Yeah.
That's dumb. Divide it by pi.
No, what you do is take the arc cosine, inverse cosine of that number. So let's see if they do that. Yeah, the arc cosine is that. And now, yeah, it gives it to you correctly. Because if you remember, the cosine of an angle is the angles between 0 and pi. That gives you all the numbers between 1 and minus 1. So this is there, so this is going to be something greater than pi halves because it's a negative value. And your calculator will give you that number, okay? If you do it in radian mode, it'll be that. If you do it in degree mode, it's something around 120, a little bit greater than 120 if my memory's right.
I got 118 in degree.
118, okay. I thought I'd say greater than, it's a little less than 120, right around 120. Okay, so that makes sense. Has to be second quadrant because second quadrant is where cosine is positive, is negative, sorry. Okay, we forgot to do that. This one, we came that close, but we can get the answer. The answer here is 3 plus 1 minus 4 over blah, blah. Who cares? Because that comes out being 0 over root 84. Doesn't matter what the denominator is. The numerator is 0. What does that tell you about the cosine of the, what does it tell you about the angle?
Orthogonal.
It's what?
Orthogonal.
Yes. And what was the angle then?
90.
90, or pi halves. Okay? Because the dot product is that, these are orthogonal, so the angle would be pi halves. Always a positive angle, and always well, of course, it's between 0 and pi. Okay. Now, this one, we didn't do this at the end either, but I think we know this one too. That would be minus 8 minus 2, which is minus 10, divided by root 20 root 5, which would be 5 root 5, which would be I said 5, I don't know where I got that, but they multiply them together. What we did before was 2 root 5 times 5 times root 5, that would be 4 times 5. 2 times 5, which is 10, and that came up minus 1. So what's the angle between those? Pi, exactly. Because theta is equal to pi, that means they're parallel lines but going in opposite directions. And also notice that means you can tell that by going back to the original and seeing that V was an extension of Z, minus 2 times Z, opposite direction. Now, here is the way I first learned what a dot product was. If you take that equation we just had, that cosine of theta is equal to the dot product of U with V divided by magnitude of U times the magnitude of V. I separated those a little bit. What if you multiply both sides of these by those magnitudes? Then you get that U dot V is equal to magnitude of U times magnitude of V times the cosine of the angle in between the two. That's how I first learned it, and that's why it made perfect sense that that was a scalar quantity, because the magnitude of U is a scalar, the magnitude of V is a scalar, and of course the cosine of an angle is a number, a scalar. It's not a vector at all. So that's how I first learned what a dot product was, and then later learned the other thing, you know, that how you did it by multiplying and adding the components, multiplying the components and adding them up. That's the way to calculate it. This is the way that it was first defined to me. It doesn't matter, but that's another way to calculate a dot product, if you know the magnitudes and you happen to know the angle in between. All right, now that leads, let me see. Yeah, oops. Example 3 they skipped. So let's go back. Okay, do example 3. Given that the magnitude of U is equal to 10 and the magnitude of V is equal to 7, the angle between the two is pi fourths. Find U dot V. What would that be? Pretty straightforward. Any ideas? Anybody? What?
It would be the square root of 100.
All right.
The square root of...
Okay. You don't need to square or square root anything. The definition is the dot product, this thing here, is this times that. All right. And this is 10 times 7 times the cosine of pi fourths. Okay? I can do 10 times 7, maybe even without my calculator. 70. And I think I can do cosine of pi fourths. Can't you? That was a Mr. Rogers statement. Okay? What's cosine of pi fourths? Root 2 over 2. Okay? Do the 2 into 70, you get 35. So this would be 35 root 2. Okay. So that's the dot product between those two vectors. Not even knowing what the vectors are. Not even caring what the vectors are. That's the dot product between the two. And it's 35 root 2. And if you did it on the calculator, you'd come up with a decimal number, which would be something about 45 maybe? No, a little less than that.
It's 49.47.
Oh, more than that. Okay. All right. Good deal. All right. Now we're ready for direction cosines. How are we doing on time? Oh, it's time to go. Oh, boo hiss. Just when we're beginning to have fun. All right. So we'll begin next time with direction cosines. And that's the top of page 773. Let's see how many homework exercises I can give you. What I can give you. Any of the odds 3 through 9, they should all be at Calc Chat. 3 is at Calc View. You could do any of the odds 11 through 17. They're all at Calc Chat. 13 is at Calc View. You can do 19. It's both at Calc Chat and Calc View. You can do any of the odds 21 through 25. They should all be at Calc Chat. And I think you can do either 27 or 29. They should be at Calc Chat. We haven't done direction cosines yet, so we'll hold off on those till later. Good deal. Let's see. And today we started in 11.2 and wound up in 11.3. All right. Any questions?